So one of the consequences of having a good understanding of how elementary row operations affect determinants is that the determinants of elementary matrices are well understood. And we can fill in this table by making the following observations. And what this table is really just tells you how to get the determinant of any elementary matrix simply by just understanding the row operation that it corresponds to. So I'll come back to this table in just a minute. Let's go through this first. So since the determinant of the identity matrix is equal to 1, well, why is that the case? Well, if you think about it, the identity matrix is diagonal. The only non-zero entries are on the main diagonal. They're all equal to 1. Well, a diagonal matrix is automatically both upper and lower triangular. And the determinant of a triangular matrix is just the product of the entries along the main diagonal. So in the case of the identity matrix, all of those diagonal entries are equal to 1. So if you multiply them, guess what you get? Positive 1. So that's the reason, right? The determinant of the identity matrix is equal to 1 for that reason. So let's start with that. Because of that, these facts, so in other words, the rules we laid out on the previous page, right? What every elementary row operation does to the determinant. The determinants of elementary matrices are easy to compute, just simply based on the row operations they correspond to. So in the case of an elementary matrix that corresponds to interchanging two rows, remember how this row operation affects the determinant. It changes its sign, right? It changes it by a factor of -1. So if you can obtain a matrix E from the identity matrix by interchanging two rows, its determinant must be -1, because it's got to be exactly -1 times whatever the determinant of the identity is, which is 1. So -1 times 1 gives you -1. That's why I can put that there. What about an elementary matrix that corresponds to multiplying a row by some non-zero constant C? Well, remember, multiplying a row by a non-zero constant C has the effect of changing the determinant by exactly a factor of C. So if your original determinant was 1 and you can be obtained from the identity by multiplying a row by a non-zero constant C, then the determinant of the elementary matrix that corresponds to this operation is just going to be 1 multiplied by C, which gives you, of course, C. And lastly, since adding or subtracting a multiple of one row to another doesn't change determinants, the determinant of an elementary matrix that corresponds to this operation, adding a multiple of one row to another, is going to be exactly the same as the determinant of the identity matrix, which is 1. So that's how we can fill this in as positive 1. So this table really just tells you how to get the determinant of any elementary matrix at all. Let's look at a few examples here. So the first one, this is a 4x4 elementary matrix, and it can be obtained from the 4x4 identity by interchanging rows 1 and 4. So it falls into the first case. It corresponds to interchanging two rows. So its determinant must be -1. What about this 4x4 matrix here? This 4x4 matrix corresponds to adding row 4 to row 1 7 times, because that's the operation that you can obtain this matrix using if you start with the 4x4 identity. So the determinant of this 4x4 matrix is going to be exactly the same as the determinant of the 4x4 identity, right? It's going to be equal to 1. Or equivalently, just think it corresponds to adding row 4 to row 1 7 times. That's one of these operations. So its determinant is equal to 1. So we can fill that in like that. What about this 4x4 matrix down here? Well, this corresponds to the operation of multiplying row 3 by -3. So this falls under this case, right, where our non-zero constant C is equal to -3. So its determinant is going to be -3 as well. Now, in all four of these cases, you can check this by cofactor expansion, right? And given how many zeros are in these matrices, it's actually not too hard to do. So it might be a useful exercise just to carefully find the determinants of these three matrices using cofactor expansion and verify that these results are true. But in the meantime, let's move on to the next idea, which is finding determinants using row operations. So we'll start with this remark, which really just lays out the main idea behind what we're going to do. So since determinants of triangular matrices are easy to compute, and the effect that row operations have on determinants is well understood, so both of those facts are established now, right? Triangular matrices, you want to compute its determinant, just multiply the entries on the main diagonal. Want to know the effect that row operations have on determinants? You've just written the rules down on the previous page. Just flip to your previous page and you have the rules right in front of you. So because of that, we can now, it's sometimes going to be helpful to use these observations to actually compute determinants. in a more simple way by just doing some row operations first. So the idea is you perform some row operations until you like what you see. Maybe you're satisfied that there's enough zeros that cofactor expansion won't be too repulsive of a task for you. It's not going to seem like it's going to be too much work. And then you let cofactor expansion take over and handle the rest. So let me show you an example of what I mean. So we've got a 3 by 3 matrix and we want to find its determinant. Okay, now we could certainly do cofactor expansion. We could pick a row or a column and just do cofactor expansion. It's only a 3 by 3 matrix. That would be completely reasonable. But let's do some row operations instead, just to illustrate this technique. So we want to calculate the determinant of the matrix A. And the first thing I'm going to do is just shift notation a little bit. I'm going to change this to 0, 1, 5, 3, negative 6, 9, and then 2, 6, 1. Okay, so, well, what row operations are we going to do? That's a decision that has to be made. And put it this way, if you're ever in doubt, you're not sure what row operations to do, or you're not sure which row operations would make your life easier, but you're also, on the other hand, you're certain that you do want to apply some row operations, it'll never harm you to work towards reduced row echelon form. So you could just start, if in the lack of any better idea, or the absence of any better idea, just start performing Gauss-Jordan elimination. So in this case, why don't we interchange the first two rows so we can get a 1 in the top left corner. So I'm going to take row 1 and interchange it with row 2. Now that's going to change the determinant, right? Performing an elementary row operation is going to affect the determinant. So we have to account for that. So on the next line, when I write equals, and then I'm going to have the result here, I'm going to write 3, negative 6, 9, 0, 1, 5, 2, 6, 1. So that's what I get if I perform that operation, right? But I'm not just performing row operations on any old matrix, or I'm not solving a system here. I'm trying to compute a determinant. So if this is going to actually change the determinant, I need to keep track of that. So, and it does, right? In fact, it does. It's going to, I interchange row 1 and 2, it's going to change I guess I'm pointing to the wrong thing. I should point to the rule on the previous page, which is where if you interchange two rows, you're going to change the determinant by a factor of a negative sign, right? And that's exactly what we did over here. So these determinants differ by a factor of -1. Well, there's an easy fix to that. Just put a negative sign in front of the second one, and now they're the same again. And now I'm not telling a lie when I write this equal sign that I'm pointing to right now, and that's important. I don't want to put equal signs between a bunch of steps that aren't actually equal, right? If that's a habit, you want to break it. Okay, well now what? Let's keep doing row operations. Well now we can simplify things by multiplying row 1 by 1/3. How about that? So we'll take row 1 and multiply it by 1/3. And that's going to have the effect of introducing a 1 in the top left corner. So I'm going to go ahead and put that there. So we're going to have 1, -2, 3, 0, 1, 5, 2, 6, and 1. So now we still have the negative out front, but what else changed here? If we take a row and multiply it by a non-zero constant, according to the rule on the previous page, if I multiply a row by a non-zero constant k, I'm going to change the determinant by exactly that factor. So the determinant of the result is equal to k times the determinant of what I started with. So in other words, if I just ignore this negative sign for a minute and just forget about what happened before, just look at these two determinants. This determinant is going to be exactly 1/3 of this determinant. So how do I make them equal again? Do I multiply this one by 1/3? No, I want to actually multiply it by 3. Because if this determinant is already 1/3 of this determinant, then multiplying it by 3 will make them equal again. But of course, since I already had a negative there, I need to just say -3. So the negative was there because it was originally there, but this 3 is to offset the fact that we multiplied the first row by 1/3. So this is to keep things the same. I think it's probably, in cases like this, it's probably easier to wrap your head around it if you just think of this way. It's kind of like we factored a 3 out of the first row and just pulled it out in front. That's I think probably a friendlier way to think about it. I prefer that way of thinking. But if you want to be strict and go by a strict interpretation of these rules, just think about it this way. By multiplying row 1 by 1/3, we cut it down by a factor of 3. So this is to prop it back up and make sure it still is the same determinant that we started out trying to calculate. Okay, so that's the first couple of operations. Next, what we can do is, well, how about we just take row 1 and subtract it from row 3 twice, and that'll make this a 0. So take row 3 and replace it with row 3 minus 2 row 1. And that will do the trick. And how's that going to affect the determinant? Well, remember, we're adding a multiple of one row to another. That's going to have no effect at all on the determinant. So that's always nice, right? Remember, if you add or subtract a multiple of one row to another, the determinants of the matrix you get in the end is exactly equal to the determinant of the matrix you started with. Okay, so what are we going to get here? We can just leave the -3 out in front because we don't need to make any other modifications to the determinant, but we will actually perform the row operation now. So we'll have 1, -2, 3, 0, 1, 5, and then what's going to happen now? 2 minus 2 times 1 will be 0. 6 minus 2 times -2 is going to be 6 plus 4, which is 10. Then we'll have 1 minus 2 times 3, that's going to be 1 minus 6, which is -5. So this is actually almost upper triangular, which would be a good place to stop, but it's not quite there. So we just need to do one more operation. Let's take row 3 and subtract row 2 10 times, and that'll turn this into a 0. Then we'll be upper triangular, and then we can just take the determinant by multiplying the entries along the main diagonal. So we will go take row 3 and replace it with row 3 minus 10 row 2. All right, so the -3 is going to stay out front. The first row won't change, right? We'll have 1, -2, and 3, 0, 1, and 5. The second row won't change either, but now for the third row, we're going to have 0, 0, and then if I go -5 minus 10 times 5, I'm going to get -55. And now we're almost done. We're essentially done because the determinant of this matrix, this 3 by 3 matrix, it's upper triangular, so the determinant is just 1 times 1 times -55. But of course, we still have the -3 out here. So to finish this off, we can just say -3 times 1 times 1 times -55. So the result, if you multiply those out, you're going to get positive 165. So that is how you can use elementary row operations to help make your life a little bit easier when you're computing determinants. Now, you could have just done cofactor expansion along a row or a column. Right? That's an option as well. But in this case, this was a good opportunity to illustrate how you can use row operations to make your life a bit easier.